Marshall posted. It'll be 2 seconds.
Wait, what?
3.3, we had 2 slides we did not get to, and they are the ones with word problems. We were discussing the properties of a quadratic. What's the vertex? What's the equation of the axis of symmetry? Does it have a max or a min? Then we got to this problem where it tied in the stuff from the previous chapters. Range, increasing, decreasing. If you're still struggling with that, let me know, and I will get that Desmos activity reactivated so that you can practice with it. I know somebody in here did the Desmos thing. Was it you? Did it help? It helps you to visualize it, so it doesn't take long, and it's a nice little visual. The answers are not written in interval notation, which is my little pet peeve. It's written in like inequality form, but it still helps you to visualize and read the range. I would encourage you to do that. All right, looking at this one right here. Everybody go to this slide. Maximizing area.
No way.
Do y'all remember the word problem from the last chapter that you had to enclose a rectangular area in the office with a set of partitions, and it was like, where can we put the partitions to maximize the area we enclose? I've lost y'all, some of you. Yeah. So this word problem right here touches on the exact same type of concept from that word problem from the last chapter. How can we maximize the area based on how much of our partitions we have? So let's look at this. We have a koi pond. Y'all know koi are those big giant goldfish-like things. A landscaper has enough stone to enclose a rectangular koi pond, same exact scenario, next to an existing garden wall. He has 24 feet of stone total. So we've talked about this. As you're reading your word problem, take notes. Make cliff notes. You have 24 feet total to work with. Not 25, not 26. Wouldn't want to build it at 23 because you have 24, right? If the garden wall forms one side, meaning this side is not important, right? There's the garden wall. What is the maximum area that the landscaper could enclose? Meaning, you would not want to hire a landscaper to come in and build you a 1 by 22 koi pond, right? That would be terrible. The fish would not be able to pass like saying, you know what I mean? You would not hire this guy. You would want to hire the guy that comes in and builds a decent sized rectangular koi pond so the fish have free room to swim. You with me? Focus. Lock in. All right. Let me delete that. Okay. So let's look at it. We're looking to maximize the area, and it says what are the dimensions that would yield that maximum area? Two things going on here. Well, first of all, what shape do we have? And what's the formula for the area of a rectangle? That's backwards. I always do LW, but yeah. I got it. All right. Length times width forms the formula for the area of a rectangle. They have already labeled our picture, but I would like you to be able to come up with this without the picture given. Let's look at it. How many feet do we have total?
24.
24. If we have a wall, we've got this rectangle. We have 24 to work with, right? In the three sides that I have to work with, are any of them equal to each other?
Yes.
This has to be equal to this. So let's call that the same variable since we know that they're equal. So how much have I used of my 24 feet so far? I've used
2W.
2W. With me?
Yep.
You got to think in terms of generic. You've got variables. I've got 24 total. I just took off a W and another W. So I have 24 minus 2W left for the length.
Unlocked.
You see how that happened? Now you can look at the picture and you can see that they already have that there.
Mhm.
So now we're plugging in. What's my length?
24 minus 2W.
Okay, and then we already know the width, right?
Yep.
It's W. That is our function for the area of this rectangular koi pond based on the size of the width. Now, if we're trying to maximize the area, what has this entire section been about? Vertex. Quadratics. Maximum is where on a quadratic? Thank you. This is a AirPod in your right ear.
Yeah, but it's not.
That's like speeding down the interstate and saying, my foot was not on gas.
That's possible though.
That wind is just pulling that car.
If I take my foot off the gas and it's still going 90,
Is that funny?
You don't need attention, you're not quiet. I know.
I know. I'm just Thank you for letting me think.
Can you use the demonstration?
Yes, no, I'll do that in a second. Oh, I'll read later. All right. We have this equation. We have it for the area of the rectangular pond. What happens if I distribute that W?
W squared.
W squared. You end up with W squared, which is a quadratic. So you can kind of see where this is going. What I like about quadratic word problems is, although the word problem will never mention quadratic, once you set it up and see that it's a quadratic function, and then you ask yourself, what's the question? It says, what would maximize the area? They're telling you, find the max of the quadratic and then interpret your answer. So we're going to find the maximum value of this quadratic. There's two ways to do that. You can go to graphing and just do the second calc max. But because these are nice, pretty numbers, what technique did I show you yesterday that's faster?
You.
For square, you can't have a W squared.
Oh.
What technique did I teach you yesterday on finding the vertex of a quadratic? Negative B.
Negative over 2A.
Winner. We can find the x-coordinate using negative B over 2A. Remember that? Yep. So now you do have to be careful here. You're going to notice that this function is not written in standard form, so don't jump with the numbers that are in front. A is not 24. A is
-2.
-2. So be careful here. If you need to, you can rearrange this, or you can come underneath and say, okay, that's B, and that's A. So we got negative B over 2 times A. Negative 24 divided by negative 4 is 6. 6 is the x-coordinate. How do I find the y-coordinate? Plug it in. So I'm going to plug in 6 into 24. 6 minus 2. Yeah. This was me finding A of 6. If you're wondering where that came from. I took a function A, I plugged 6 in. Everywhere there was a W. And I got 72. Now, here's where you've got to know what you're reading. Here's where it drives me crazy when people can do the math, they cannot tell you for the love of anything, like what the numbers mean. It is the vertex. You need to understand what the graph would look like. The graph sorry. Okay, the graph, no matter where it is, like in terms of, we're talking about length of something and then area of the pond. So your input value was W. That determines your width, right? And your output value is A, which determines your area. So if I found the vertex to be 672, I'm going to go right 6 and I'm going to go up 72. If this is 672, what does that actually mean in terms of the problem? We'll read the graph. What's the x coordinate? So what's the 6? The width is 6. When the width is 6, the area will result in 72 square feet. Because area is where you're multiplying the two things together. So let's put it together. The width would be 6 feet, which means the length would be, go back up to your picture. How do you get the length? I heard it. What'd you say?
Plug it in.
Plug it in. So 24 minus 2 times 6. 24 minus 12 is 12. And that would result in an area of what? Square feet. We talked, excuse me, we talked a lot there. Let me recap. Let me recap this whole problem. We had a wall we didn't need to worry about. We had 3 walls we did need to worry about. We have 24 feet total. We came up with expressions for the 3 walls we need. We set it into the formula for the area of a rectangle. We recognized it's a quadratic. It asks for maximum area. That would be the vertex. You can graph on your calculator and try to find it, or you can take the vertex formula that we learned yesterday. That gives you the x coordinate of the vertex. Now I wrote x here. Technically it's w because this up here is w. So if you're worried, if you're confused why we had w and now we switched to x, I just put x because yesterday we called it x equals negative b over 2a. Then you take that coordinate and you plug it into your area formula to get the actual area. To get the other side of the rectangle, you've got to plug it into that expression you came up with. Welcome to college when there's like 12 steps involved. Well, you can, but if it were me, I would go with what you got right here in case you messed up 72. What if you plugged it in wrong? Yeah, just as equally, yes. All right, look at the next one. This is one of my favorites. No, it's really not, but it intimidates people. I don't know why, but it's one of my favorites because it is the same concept, but it appears all the time in higher level math classes. All right, so, see my drawing? It's all right, I'll draw you another one. A model rocket is launched with an initial velocity of 100 feet per second from the top of a hill that is 20 feet high. Its height in feet t seconds after it's been launched is given by this function. Determine the time at which the rocket reaches its max height and find the max height.
Jack, how are you so smart?
Well, if you're picking up on all the signals I'm dropping, we've talked about quadratics, we learned the vertex. I'm throwing a word problem at you. It's the vertex of a quadratic. Now, let me, yes. Now, what I need you to understand is the path of the rocket is not the quadratic itself. The quadratic is what appears as time passes while the rocket is in air. You could take a ball and throw it straight up in the air and it comes straight back down, which means it never did this, correct? But because it went straight up in the air and came straight back down over the course of time, if I graph it, it's going to look like a quadratic, which is a very misconception in math. People think the quadratic is the path of the rocket. It is not. Quadratic is its relation in terms of time, as time is passing, and where it is in the air. Okay? All right, so if you need a visual, I got you. There's our cliff. All right, here's Pierce. All right, here's Brody.
Hey.
Which one? Oh, see.
Who hits the ground first?
No. Oh. All right, we have a rocket. Right?
Crazy.
We got. Here we go. We got a rocket. He's sent it off into the air. You with me? Still with me? The rocket is going to go off into the air, and then it's going to hit the ground. Right?
Nice rocket.
Let's go through. We're pressed for time. I could draw something better, but we're pressed for time. Let's go back through and pull out information that's necessary. First of all, is this physics class? No, this is not physics class, okay? So the fact that it's traveling at a velocity of 100 feet per second is really not relevant here. And the reason why is because they are giving you the function. You're welcome. You don't have to create it. The hill is 20 feet high. Does that matter? Does the height of where he started to project the rocket change, like, our final answer in terms of how high?
No. Wait.
Yes.
What'd you notice? It's already in there. So while it is relevant, what have they already done? They've already put it in there. So it doesn't really matter that it's 20 feet high because they've already taken it into account in our function. Which is why when you get these word problems, I don't mind them because I know to look at the function. There's a lot of unnecessary stuff in there that I don't need. But you do need to know your two variables. What's t? In, this matters. And then what is s of t? Read the problem. You're right. It's the height in feet. It's the height in feet. It says determine the time. That means find what? Find t in seconds at which the rocket reaches its what?
Maximum height.
What's the part of the quadratic that is always at the max? The vertex. The vertex. Right? And what did I teach you yesterday on how to find the vertex? There you go. So let's find. Now, I'm going to say x, but we don't actually have x. We have what? T. So when I write that, please don't get confused. The formula from yesterday was x equals negative b over 2a, but our input is actually t, not an x. All right, let's do it. Negative b is what? 2a. What's a? So negative 100 divided by negative 32. We are going to go to, let's go to the nearest hundreds. What'd you get? I've run out of room. 3.13 seconds. So the rocket will be at its highest point at exactly 3.13 seconds. And then the next question is, what is the highest point? How do I find it?
Plug it in.
Plug it in. So S of 3.13. Now mine's going to be a little off because I did 3.125. But you should get close to this, right? About 176 feet. What is it not drawn to scale? Not drawn to scale at all. Okay, so now how do you actually like write it out? You would say that the rocket has a max height of 176.25 feet at 3.13 seconds. Like that's the well-rounded way to wrap up your word problem. Really not that bad, and they are the same thing every time, but it might not be a rocket, it might be a rock, or it might be a ball, or it might be a projectile. You woke up and chose violence today, didn't you? I have one more slide on here. It says, I think it's My Math Lab. Oh, it was, I think the reason I put this on here, remove the trash, that's for me. I'll take care of that.
How about it be grateful?
Okay, look at this. You're going to want to take a picture or come back to this video at 21 minutes. Number 10, when you do number 10, please make sure that you pay attention to the folding of the object. It is not a koi pond per se, but now that I think about it, it could be like a koi pond because you've got, if you notice, you're taking a piece of paper, you with me? 8 by 20. You got an 8 by 20 piece of paper. You're folding it to form a U shape, stay with me, but obviously bend, to form a U shape, and they want you naturally to have the sides level. They don't want a lopsided U shape, you with me? They want it level. So that would mean whatever this is, then this is, correct? Okay, so that's what I'm going to label as X. Because I don't know it, but I know they have to be equal. Which would mean that this down here would be the remainder minus the 2X. So that's why you can see where I'm saying this was 8 here. That would be 8. That would be 8. And then you can see that jutting up is X, and then that would be X. Please try it. It's really not that much more challenging than the koi pond. And I'm even giving you the hint that it's folding like this and where to label. Please try it. If you get stuck on it, you can ask me for help tomorrow. Number 11, I was just reminding you of the formula of the area of a triangle in case that has left your memory because it's been a while. A 1/2 base times height. This should look very familiar. This is exactly like the one from the last chapter, but this time instead of evaluate how much profit they would make if they sold $800 worth, this time it's where would they make the most profit. Again, it goes back to what did we learn in this whole section? The vertex of a quadratic tells us everything we need to know. So you're going to have a quadratic. You're looking for the vertex. You just have to know how to interpret the vertex. The x-coordinate is one variable. The y-coordinate is what you get when you plug that in. Okay?